Hello guys, today I'm gonna present on a topic conduction of heat and my name is Anjan from Audi section. Conduction of heat, a fundamental concept in physics and maths engineering, plays a crucial role in many aspects of our daily lives. What is conduction heat or heat conduction? Heat transfer. Heat conduction is one of the three main mechanisms of heat transfer alongside convection and radiation. Energy transfer. It involves the transfer of thermal energy through direct contact between molecules without any matter of movement. The importance of heat conduction. Everyday life. It's essential for heating our homes, cooking food, and even the functioning of electronic devices. Industry. Heat conduction is crucial for various industry processes such as heat metal casting, heat exchangers, and thermal insulation. Fourier's law of heat conduction, mathematical description. Fourier's law defined the rate of heat transfer through conduction as proportional to temperature gradient and the area of heat transfer. Temperature gradient. The temperature difference between 2 points is driving force behind heat conduction. Thermal conductivity. This property represents the ability of a material to conduct heat. A higher conductivity indicates a faster transfer of heat. The thermal conductivity coefficient. Its material property. The thermal conductivity coefficient is a material property that quantifies its ability to conduct heat. It's measured in units like W per meter Kelvin. Impact on heat transfer. Materials with high thermal conductivity, such as metals, transfers heat quickly, while materials with low thermal conductivity, like insulators, resist heat flow. Applications of heat conduction. Energy production. Power plants are used heat energy conduction to generate electricity by transferring heat from a source like fossil fuels or nuclear fission to working fluid. Transportation. Car engines rely on heat conduction to transfer heat from combustion process to the cooling system preventing overheat. Renewable energy. Solar panels use heat conduction to transfer heat from the sun to photovoltaic cells, which then generate electricity. Building design. Thermal insulation uses materials with low thermal conductivity to prevent heat loss in buildings, reducing energy consumption. Steady state versus transient heat conduction. Steady state. In steady state conduction, the temperature at any point in a material remains constant over time. Transient. Transient conduction occurs when the temperature at a point in a material changes with time, typically due to a change in heat source or boundary conditions. Fourier's law of heat conduction. Foundation of heat transfer. Fourier's law describes the relationship between heat flux and temperature gradient. Directional flow. Heat flows from regions of higher temperature to regions of lower temperature. Material properties. The heat flux is proportional to thermal conductivity of the material. Mathematical representation of Fourier's law. Q is equal to minus K into dt by dx, where Q is the heat flux, K is the thermal conductivity, dt by dx is the temperature gradient. It is also known as rate of change of time with respect to area is the temperature gradient. Mathematical formulation. The heat conduction equation, often represented as Q is equal to minus Ka into dt by dx, quantifies heat transfer. Here, Q represents heat transfer rate, K is thermal conductivity, A is cross-sectional area, and dt by dx is temperature gradient. Engineers utilize this equation in simulations to predict heat flow in the system. One-dimensional steady-state conduction. One-dimensional steady-state conduction occurs when temperature distribution does not change with time. This scenario simplifies analysis since the heat transfer remains constant across the section. Engineers often use this model for analyzing heat flows in walls, pipes, and other structural materials. Multidimensional conduction. Multidimensional conduction involves heat transfer in more than one direction, complicating the analysis. Engineers must consider boundaries, conditions, and material properties in these scenarios. Numerical methods and finite element analysis are often employed to solve complex heat conduction problems. Derivation of heat conduction equation. Energy balance based on the conservation of energy. Fourier's law. Substituting Fourier's law into energy balance. Partial differential equation resulting in the heat conduction equation. Boundary conditions in heat conduction. Prescribed temperature. It specifies the temperature at a boundary surface. Prescribed heat flux specifies the heat flux at a boundary surface. Convective boundary condition relates the heat flux to temperature difference between the surface and the surrounding fluid. Convectional boundary condition, it is equal to minus k into dt of 0 comma t divided by dx, which is equal to h into t of infinity comma 1 minus t of 0 comma t, where dt by dx is the temperature gradient at surface k per meter, k is the material conductivity, h is the heat transfer coefficient. Analytical solution to heat conductivity equation. Steady state. Temperature is constant with time. Transient. Temperature varies with time. One dimensional. Heat flow in single direction. Conclusion and future perspectives. Understanding heat conduction is essential for engineers to enhance energy efficiency and performance. Ongoing research aims to develop advanced materials with tailored thermal properties for specific applications. As technology advances, engineers will continue to innovate methods for optimizing heat conduction in various fields. Thank you.